All right, welcome everybody to the next to the last super seminar of this semester. So today we will have three early career speakers with speaking for 20 minutes each. And let me just remind everybody that next week, a week from now, we will have three more early career talks. So please come to those also. And today, we start right away with the Kamya Amini from Virginia Tech, who will speak about a bridge between the quantum K-theory of the Grassmannian and that of its cotangent bundle. So please go ahead.
Okay, hello everyone. Thank you very much for the opportunity to speak here. So today I want to talk about the specific relation between the quantum K theory of the Grassmannian and its cotangent bundle. And I will start with some basic definition, and I start with the definition of the K ring. So assume that we have a T variety X where T is a torus. The equivalent K ring of X it's a set of all equivalent vector bundles on X, where the tensor product is the multiplication in this ring, and the formal sum is just the addition in this ring. For any short exact sequence, we have a relation in this ring, such that for this short exact sequence, the class of the middle one is just sum of the other vector bundles. So to each vector bundle, we can assign a class which called Herzebuch class, which is just the sum of the wedge powers of the vector bundle, and we define this y to keep track of the decrease. Also, we have some version of the localization theorem that tells us that if the torus fixed point of the our space is finite, we can write any K-theoretic class in a special basis called fixed point basis. So all you need to know is just the restriction of these classes to the fixed points. Okay, now I want to define the quantum K ring of X, where X is the projective smooth variety, and for that I need the modular space of stable maps. So this is just one of the compactification of the set of maps from the projective space to the variety X. It parameterizes the set of maps from a genus 0 nodal curve with n marked points to our variety X, such that the push forward of the fundamental class of the domain curve is a fixed effective curve in the second homology of our variety. We also have n evaluation maps. If I have a map in this modular space, because the domain is a pointed curve, I can evaluate the map at the ith mark point. So we use this to define the K-theoretic Gromov-Witten invariance. If I have n K-theoretic classes, I can define the K-theoretic Gromov-Witten invariance as an Euler characteristic of the pullback of these classes via these evaluation maps. So for an example to keep in mind, if I have some yi, which are the subvarieties of X, and if I consider alpha i's to be the class of the structure shift of those subvarieties, these invariants are just some virtual count of degree D genus 0 curve that passing through these subvarieties. Okay, we use this invariance to define the quantum K ring of a smooth projective variety. It was introduced by Givental and Lee in early 2000, and it's the deformation of the K ring that we had. So as a module, it is just a set of power series in Q. This Q can be vector, it can be several Novikov variables. So as a module over KT of points, just set of power series over Q. We can define the pairing on this module using 2-point Gromov-Witten invariance, and we use this pairing to define the quantum product of two classes alpha and beta in a way that we pair it with the third class, and their pairing should satisfy this relation defined by now 3 points Gromov-Witten invariance. One of the main important function in the enumerative function in the quantum K ring of a variety X is the J function, which is the generating function for 1 point descendant chromosome with an invariant. This descendant, it just means that you also add these cotangent line bundles on the modular space. So formally, you can define it as to be this power series if you choose a basis for your kt of x by phi i's. If you expand this to the power series, it will encode all of the 1 point chromosome with an invariance. So the importance of this function is that it governs the quantum scaling of your variety in a sense that if you have some Q difference equation D, which is based on some parameters, and if this operator annihilates your J function, so if I act on the J function, I get 0, after some specialization, which you can see here, we can get a relation in the quantum scaling of our variety. And here, just this Q to the power of Q partial Q, just the operator acting on the function of Q by just shifting capital Q with Q. And this P is just the class of the line bundle. So the important thing is that you can get some relation by using the J function. So let me give you an example. So the quantum scaling of the projective space is known. As an algebra, it is generated by O of -1 and O of 1, and we have one relation, very similar to the quantum cohomology of Pn. So these lambda i's are the equivalent parameters of the torus that we act naturally on Pn, which is C star to the n plus 1. The J function of P1 is also known in the equivalent case, and it is given by this power series. And the important thing is that you can easily check that it satisfies the following Q difference equation. So we have this relation for the J function. And if you use the previous theorem that I call it IMT, so you need to do the specialization, which is just you replace this numerator with the tautological class of P of -1. And you get this relation in the quantum scaling of the projective space that we already knew because of this presentation. Okay, now how can we find some formula for this J function? So it is hard to work on the modular space of stable maps. So we want to work in an alternative compactification of the set of maps. Now I just focus on the Grassmannian. An alternative compactification that we have is the Grothendieck quota scheme. So it's parameterizing the degree D rank n-r coherent quotient of trivial bundles on P1 for fixed D. You can also take the kernel of this quotient and consider these short exact sequences. So the quota scheme just parameterizes these short exact sequences. Also note that naturally C star n acts on Cn. Also, we have an extra C star which acts on P1. So this large torus naturally acts on the quota scheme. Okay, now Typal showed that we can use this quota scheme to define find some formula for the J function. She considered a special C star fixed loci of the quota scheme, which are points that supported on 0. And it is known that these C star fixed loci is just a union of some flag varieties. And the J function is just a push forward of the class of 1 over lambda -1 of the conormal of these fixed loci inside the quota scheme by these flag bundles that we have from this union. So the point is that we can transfer the calculation of J function to the quota scheme. And we can use this to find the localization or restriction of this J function at any fixed point of the Grassmannian. So if you do some calculation, which you need to find the tangent space of quota scheme and find some weight space decomposition of those modules, you can see that the restriction of the J function at each fixed point is given by these some kind of a scary function. So the main point to remember is that so the terms in this localization are just 1 over 1 minus some monomials based on the equivalent parameters and the weight Q. Okay. Now I want to go and see what can we say about the cotangent bundle of the Grassmannian. So first I want to explain a quiver type definition for the cotangent of the Grassmannian. For that, consider V to be the set of pair of matrices such that the multiplication is 0. It has an action of GLR of C. Inside V, I consider the semi-stable point of V, which consists of pair of matrices such that A has a full rank. And you can define the cotangent bundle of Grassmannian as just the usual quotient of this VSS by the action of GLR. Okay, now we want to consider the set of map from the projective space now to the cotangent bundle of the Grassmannian. Okay, note that based on the definition that I gave you, this cotangent bundle of the Grassmannian is some quotient, the quotient of VSS by GLR. So we can consider this stack quotient now V quotient by GLR. And it is known that this cotangent bundle of the Grassmannian sits inside this quotient stack as an open set. So we can consider the set of all maps from the projective space into this quotient stack. So again, we have evaluation maps for any point P in the projective space. I can evaluate function f at that point P. It lands on the quotient stack, but if for some point P it lands on this special open set, which is cotangent bundle, we call that P is non-singular point of the, or say we say that f is non-singular at this point. There is also a well-defined notation of degree for quasimaps, and we can decompose the quasimap space based on these degrees. For a fixed degree D, these spaces has perfect abstraction theory, so we can define the virtual tangent bundle and the virtual structure shift. Okay, so now in this setting, one of the important enumerative function that we have is the quasimap vertex function. So they are just a generating function for the just virtual count of the quasimaps to the cotangent bundle. You can also define them by just pushing forward the structure shift by the evaluation map at some special points here, for example, infinity. And you can use the just localization theorem to see that they are really the same. Okay, so Pushkar, Esmirov, and Zeitlin tells us how can we localize this vertex function at any fixed point of the cotangent bundle. And so for any fixed point of the cotangent bundle, we again have a localization of the vertex function, which is given by this function, which is again some complicated function. But we have formula for that. So now we have the J function. We know what are the localization at fixed points. We have the vertex function. We have the localization at each fixed point. Now we want to see how can we relate them together. Okay, note that because we restrict to fixed points, so they live in the K ring of some point. So I want to explain some operator on the K ring of a point for some torus T cross C star. Okay, so assume that R is the K ring of a point with this torus, big torus here. I define the multiplicative set inside R to be the set of finite product of polynomials form 1 minus P, where P is a monomial. I localize R at this A, and I consider the special subset of this localized ring. So I want to define a balancing operator beta y on this set U. So, and you can see here that I defined it here. So the point is that whenever you see the terms 1 minus P, just divide it by 1 plus YB. So geometrically, you can think of it as this finite product of 1 minus P are just lambda minus 1 of some modules. And when you divide by these products, you just divide it by lambda y of that modules. So you can also extend this to the all u, and also you can extend it naturally by acting on the coefficient of any power series in Q. Okay, now we have some results here. So we have the vertex function on the cotangent bundle. So note that this vertex function has this extra h, which is the weight of the extra C star action that acts on the cotangent bundle and to related to the cotangent direction. So I'm in the cotangent bundle. If I set this h equal to 0, if I look at the limit h equal to 0, I descend to the base, which is the Grassmannian, and I recover the j function by just in the limit h goes to 0. So this is one thing that we have. So, and the second thing that we have is that we can reverse this procedure. We can start from the base and start from the j function. And if we, so remember that this j function has the terms of 1 over 1 minus some weights, which for monomial. So I can apply this balancing operator. And if I do that with very simple change of variable, that I set y equal to minus q to the power minus 1h, I will recover the vertex function. So I can lift the j function from the base to the cotangent bundle. And so it says that, so the balancing of the localization of the j function will exactly give you the localization of the vertex function. So here, as an example, I just do the balancing for the j function. So if you do the balancing of the j function that we saw in the previous pages, the balancing of the j function for each d is given by this formula. You see, we have 1 minus some terms here. I just divide by 1 plus y, and so it will come to the numerator. So this is the balanced j function. And if you put y equal to minus q to the power of minus 1h, you will recover the vertex function. Okay, so this is about the classes. Now, if you remember, I told you that this j function satisfied here for projective space, satisfy these q difference equations. Okay, we balance these classes. Now, what can we say about the operators? We can also balance the operators, and you may guess what should we do. So whenever we have operators of this form, 1 minus some monomial, I can divide by now 1 minus h of that monomial. The similar construction. So we can balance the operators, and we can also balance these classes. So, and the point is that these balancing are compatible with each other. So the theorem is that if we have, this is for j function, it's satisfied for more general classes and difference equations. So if you balance this q difference equation, we will get this operator, and if we balance the j function, we get the balanced j function. And the claim is that this balanced j function satisfies this q difference equation.
2 minutes.
Sure. Okay, so we can rewrite this equation as when you can multiply this equation by from the left by the denominator, and you get this q difference equation. Unfortunately, we don't have IMT theorem for the cotangent bundle and quasimap, but still we can do this specialization that we change these numerators by just p. And if you do this, you will get these equations for projective space. And these are very important equations in the mathematical physics and integrable system. They call Bethe-Ansatz equation for cotangent bundle of the projective space. And they are expected to be the relations in the quantum K-ring of the cotangent bundle. I didn't define the quantum K-ring of cotangent bundle, but it is accepted to be the relation, especially in the full flag varieties, the Pushkar, Zeitlin, Smirnov, and Korotev, I think, proved that for cotangent bundle of the full flag varieties, especially here for cotangent bundle P1. These Bethe-Ansatz equations are really the relations for the ring. And so by this idea of the balancing, we can recover these Bethe-Ansatz equation, which suggests us that maybe there is some IMT kind type theorem for the cotangent bundle and the quasimap space. Okay, I can stop here. Thank you so much.
Very nice thought. Let's thank our speaker